Mate, wait up. What are you trying to do? You're going to vandalise the concrete.
Mate, I'm trying to make some green concrete to save the environment.
Look, that is a good cause, but that's not how you're going to make green concrete. But I can tell you how to make green concrete.
Let's have a look at the history of green concrete. First, in 1966, fly ash was first recognised for its pozzolanic properties in use with cement. Then, in 1972, the potential and use of slag was established in the cement industry. Nearly 2 decades later, the term green concrete was coined, and further research into developing a more sustainable and environmentally product accelerated. Then, in 2008, the introduction of chemical admixtures began. Most recently, specialised products such as Envisia began joining the market as purposefully designed cement mixtures with a low carbon footprint. There are a number of substances used to reduce the carbon footprint of concrete by replacing the clinker in concrete production. These are called supplementary cementitious materials, or SCMs for short. These include ground granulated blast furnace slag, fly ash, and amorphous silica. Blast furnace slag is an industrial waste made in iron production which can be repurposed to replace a portion of the cement. When converted to a powder, ground granulated blast furnace slag forms a compound chemically similar to cement, composed predominantly of oxides of silica, magnesium, calcium alumina, and lime. This has a number of effects on plastic and hardened state properties, including but not limited to increased setting time, increase in long-term compressive strength, reduced permeability, reduced creep. Another SCM is fly ash. Fly ash is a waste product formed from the burning of black coal. This fine residue is made up of small spherical particles varying in size. It is mainly distinguished by its low carbon content. However, it is graded based on particle size, loss of ignition, moisture content, and SO3 content. Its effects on concrete can include improved workability, possible reduced water content, improved cohesion, increased hardened state compressive strength, decreased permeability. Amorphous silica. Amorphous silica is an industrial product collected from the refining of silicon metal as condensed silica fume. These silica particles are submicron in size and spherical in shape, forming a very fine powder or slurry when mixed with water. In practice, amorphous silica is commonly used in conjunction with fly ash and slag, acting as a fine filler. Some of its effects on the properties of concrete include reduction in bleed, decreased paste permeability to acid, chloride, and sulfate attack, increased cohesion, increased setting time, and increased hardened state compressive strength. The properties changed by the inclusion of these SCMs can give a concrete blend both advantages and disadvantages over general purpose Portland cement. Their use, however, is increasingly due to their technical, environmental, and in many cases economic benefits. Beyond this, fly ash and slag can also reduce the costs of production, while amorphous silica can cost significantly more than just ordinary Portland cement. Recycled water can be used in order to reduce the amount of water used in concrete suitable for other purposes or reduce the water demands on a population. This has become a universal practice in a number of places, including Australia. The main concern with the use of recycled water in concrete is the contamination of the concrete by impurities in the water. This can have effects on the hardened state properties of the concrete and so must be tested and accounted for in design. It is the reason Australian Standard 1379 requires any water to be drawn from a source of acceptable quality. The acceptability of a water source, according to AS 1379, is tested using test samples of concrete mixed with a known acceptable source of water and the untested water. In order for a sample to be used, it must demonstrate a compressive strength after hardening of at least 90% of the known sample. The setting time of the unknown sample must be not more than 60 minutes faster or 90 minutes slower than the known sample. The failure of these tests can indicate significant detrimental impurities which can affect the concrete short and long-term properties. Some of the relevant standards for green concrete include the methods for testing concrete produced in AS 1012. Alternative aggregates must be tested in concrete against AS 3600. Aggregates for engineering purposes and testing are covered under AS 2758.1 and AS 1141 respectively. The specification and supply of concrete against AS 1379 and the supplementary cementitious materials used under AS 3582.
Chemical admixtures are the modern world's answer to sustainable production of concrete. With the use of 4 different types of main additives, a normal batch of concrete can become more environmentally friendly and reduce waste from their landfills. The 4 main types of chemical additives include water reducers, which are normal range, mid-range and high range, retarders, accelerators, and air entraining agents. A superplasticizer is the most commonly used chemical admixture in today's green concrete development due to its beneficial nature. As you can see, a batch of concrete with a water-cement ratio of 0.35 is inconsistent and hard to work with. With the addition of a dry superplasticizer, the concrete becomes increasingly more workable and fluid-like. Superplasticizers are classed as high-range water reducers and aren't necessarily sustainable by themselves, but in the combination of SCMs and recycled materials can be used for non-structural sustainable purposes. Using this admixture, it clearly shows how we can increase the workability and pumpability, hence creating an easier to place and stronger batch of concrete. The major companies leading the charge into more environmental focused developments are both Boral and BASF, which supply and develop a large amount of sustainable chemical admixtures, including the following. Hence, therefore, the chemical admixtures are a major component in designing sustainability for the future.
Aggregate provides a large cost benefit and improves properties. Aggregate accounts for 60 to 75% of the volume within concrete. It plays a major part in the strength, durability, and amount of shrinkage during drying. Aggregate must have a range of gradings in order to enhance these properties.
Traditional aggregates include sand, river gravel, and quarries, while manufactured aggregates include recycled plastic, recycled glass, blast furnace slag, steel punching, recycled crushed concrete. Pictures can be shown of these examples. Grading is an important aggregate property. A wide range of gradings is essential to improving the properties. Well-graded aggregate reduces voids in concrete and enhances the strength. It is important to have a consistent grading graph which can be shown on the left in the image, and on the right is the range of aggregates showing the reduced voids. This is an example of sieving through and grading out. Particle shapes and textures of aggregates affect the overall packing of aggregates and the workability of the concrete. The texture of the shape mainly comes into play when looking at the water-cement ratio. For example, a honeycombed, elongated aggregate would require more cement paste to fill the void. Strength and durability is measured through the wet-dry factor, which contributes to the overall strength of the concrete. The wet-dry is a test which measures how much mass of aggregate needs to be crushed to produce 10% of the original mass in fines. Abrasion is the ability for the concrete to be able to resist worn by friction. Skid resistance of the concrete will have in its hardened state. On the left, the British pendulum test.
The Los Angeles abrasion test is shown on the right-hand side. Aggregates play an important part in the dimensional stability of concrete, as it makes up over 60% of the volume.
This looks at the shrinkage of the concrete. It is important to minimize the shrinkage, as this can lead to cracking. The graph demonstrates the difference between the aggregates of blast furnace slag and basalt. As you can see, blast furnace slag is better. For the alkali silica gel to form, two components are needed: cement and aggregate with a certain mineral to react with the alkali. Minimizing reaction by having low alkali cement or reducing the cement content through use of SCMs. The photos demonstrate the side effects of what has happened when this reaction occurs.
There are many applications of green concrete despite having differing mechanical properties such as lower strength or a small modulus of elasticity. Some different types of green concrete include polymer concrete, geopolymer cement, and lightweight concrete. Geopolymer concrete is a type of concrete that uses polymers to replace lime-type cements as a binder. In some cases, the polymer is used in addition to Portland cement to form polymer cement concrete. In polymer concrete, thermosetting or thermoplastic polymer resins are used as a principal polymer component due to high thermal stability and resistance to chemicals. Polymer concrete may be used for new construction or for repairing of old concrete. Polymer concrete has historically not been widely adopted due to high costs, but recent developments have seen the costs go down. Geopolymer cement is a binding system that hardens at room temperature, like regular Portland cement. It is being developed and utilized as an alternative to conventional Portland cement for use in transportation, infrastructure, construction, and offshore applications. It relies on minimally processed natural materials or industrial byproducts to significantly reduce its carbon footprint, while also being very resistant to many common concrete durability issues. The left picture shows the hardening of Portland cement through hydration, while the right figure shows the hardening of geopolymer cement through polycondensation. Lightweight concrete, also called foam concrete, is a versatile material which consists primarily of a cement-based mortar mix with at least 20% of volume air. This volume air comes from a foaming agent that is mixed with the cement binder to form the concrete mix. The material is now being used in an ever-increasing number of applications, ranging from one-step house casting to low-density void fills. Generally, it has more than excellent thermal and sound insulating properties and a good fire rating. Depending on the type of green concrete it is and what is in the concrete mix, green concrete can be used in many applications from fire resistivity to protection against chemical attack. Australia has begun introducing greener concretes recently, and another example where green concrete has been used extensively over the years is in Denmark. Constructed between 2004 and 2006, the Council House 2 was awarded the Australia's first 6 Green Star rating in April of 2005, the maximum possible score. The building was constructed using an approximate total of 6,000 metres cubed of green concrete. The review of the design amassed a total of 80 out of the possible 140 points, with green concrete contributing up to 2 out of the 3 possible concrete points for the materials section. The building boasts an 85% reduction in electricity consumption compared to the existing council house of similar size, a strong statistic comprised by the strong contributing effect of green concrete. Similarly, Denmark's first carbon-neutral building, called the Green Lighthouse, utilises green concrete to help achieve its sustainability. In the hopes for Denmark to become more green and to help reduce the country's CO2 emissions due to concrete to below 1%, Denmark built the Green Lighthouse and are now moving their focus to more sustainable building practices. Green Lighthouse has also been given a LEED Gold rating, obtaining 68 LEED points, with green concrete contributing to some of the points awarded. The Green Lighthouse boasts similarly to Council House 2, utilising facade windows to reduce heating costs and having a drastic decrease in energy costs while compared to buildings of similar size.
So Joshua, do you now understand the importance of green concrete and the effects it has on society?
I think I do. Thank you, Tom. Won't be needing this anymore.